So today we're going to talk about periodic law. This will then lead into the trends on the periodic table, and it's all pretty cool. But then we're going to talk about easily the coolest periodic table ever, and then we'll finish this video with the jerks of the periodic table. Okay, so periodic law by these guys, Meyer and Dmitri, now, or Mendeleev, they came up on this independently. But first, the law says that the physical and chemical properties of an element recur, which means they cycle around again, in a systematic and predictable way when they're arranged in order of increasing atomic number. Okay, so these guys came up with the law independently in 1869, and Meyer based his on the atomic volume, which is cool. This is an interesting thing, whereas Mendeleev's was a bit more generalized, and he noticed it across many more different properties, but Meyer noticed it on one, and he stuck with it, and that's fine. And he worked it out on the molar volume, which is basically the atomic mass divided by the density of its solid form. Okay, so the volume of it. So we've got a molar quantity, a molar mass, which is, the mass of a certain number of atoms. Molar volume is the volume of a certain number of atoms, which is cool. Alright, so this is Meyer's graph. Lothar Meyer is his name. And you can see he's period 1. And then, next period, next period, and so forth all the way up, which is pretty cool. Alright, now, this is the coolest periodic table ever. And we'll get to why. So, Alexander Emile de Berger de Chateautois, whatever. I can't say his name, clearly. It's his fault for being French. This is the telluric helix. And it's pretty cool. This is my favorite. So here's a French geologist, not so interested in metals but more classic rock, and he noticed that groupings of certain elements. So he noticed that certain elements grouped together, but what he really noticed was their periodicity. Now, again, he wasn't as refined. He wasn't as specific as the other guys, and that's part of the reason that he was kind of ignored for a little bit. So he was the first to arrange chemical elements in order of atomic weights, and he did this in 1862. Now, de Chateautois, whatever, only published his paper, but he didn't include this wonderful graph here, this magical graph that we love, or I love, and you hopefully will love. He didn't include it. I don't know why. So periodicity was imposed on the elements based on physical similarities, thanks to his studies in geology. That's where most of these metals, but most of them come out of the ground. So basically what he did was he went, you guys look similar, that's a group of, say, 16. You guys look similar, that's another group of 16. And he just did this all the way down, and then lined it up according to the atomic mass down the side, which is awesome. He was generally ignored, both as his graph wasn't published, and he was published in this prestigious geology journal, so as opposed to a chemistry journal. Alright, but this is what it looks like. So this is his messy graph. You're like, sloppy guy. Dude, come on, tighten up. But here's what a neat one looks like. So you see you've got 16 squares across the top, and if we then just go atomic mass on the way down, go and it increases up to 16 as you go down, and it starts again, and it's cool, it's simple. But what it shows you is the first recurring pattern. And if you look down the side here, well, I'm pointing as if you can see my finger. If you look down the side here, things start to appear in there, what we call their groups, so the columns. And that's pretty awesome. And that's the telluric, as also tellurium was in the middle, like he was the midpoint. But that's the telluric helix, and that's a cool one. So lanthanides, jerks. All right. So the reason they're a jerk is that they were really hard to work out, and weren't worked out until I think the I want to say 1920s, maybe 40s. I don't know. But they throw out periodicity. Basically, they all exist right here, the lanthanides, and physically, they're all almost identical. They're really hard to tell apart. The actinides beneath them, they're all really different. They work periodicity. That works just fine for them. But the lanthanides really throw stuff off. So then what we call an exception. Wrong. Wrongity wrong. Okay, so laws don't have exceptions. Not in science. What they have is incompleteness. Ignorance, if you will. So this is a case where we have some ignorance to periodic law that's yet to be uncovered. We don't know what it is. If we did, we'd fix our periodic table. But there are no exceptions. Remember that. That's important. There's stuff we don't understand. So if your theory or law in science doesn't completely generalize, then it's incomplete or wrong. It might be good enough to suit the model, to suit what we need, but it's not 100% accurate. That's us for today. I hope that made sense. Next, you're going to look at some images and watch a little video on periodic trends, and all will be golden.